So what is this man? So there is a satellite called Farmi satellite, and this is actually what the Farmi satellite has observed by observing the entire sky in gamma over 5 years. So if you see this whole bright patch, that is actually a galaxy, and this bright patch is because we actually get a lot of gamma radiation from objects in our galaxy, and here you see this lot of small stuff. They are actually the extragalactic gamma ray sources which the Fermi detected. So I will focus on one class of them later on. But first, at the outset, I want to note that this is not very not even like the optical sky, because while this looks like so, it is actually very variable. Actually, I cannot show the animation here, but actually, if you think actually each point there, the big or small point, they actually change their animation over a very short time scale. So if you see the animation, you could see. So this is actually very variable, and one needs to look at it from a different point of view. So why are we just focusing on high energy type at all? That's high. So first of all, it is a probe to the non-thermal universe. By non-thermal, I mean that the processes here they are not in thermal equilibrium with the surrounding. So you cannot display the spectrum like an Maxwellian spectrum like that. So for most cases they follow power law spectra. So and from them we can get the physics of a lot of high energy processes, for example synchrotron, inverse compound based processes like that. So there are a lot of these gamma rays comes from their various types of sources. For example, for extragalactic sources, you have active galactic nuclear gamma ray bursts. If you consider galactic sources, then there are supernova events, and as well as there is a diffuse background always present from the galaxy. So all these research is made by gamma ray astronomy are discipline in its own right, and it has now established links to astroparticle physics and cosmology. So in this talk we focus on gamma rays with energies greater than kT, which means that in this region the dominant interaction channel for photons is the electron positron pairs. So currently the highest energy detected, this is detected simply from a DEP laser for 1 years. So that is 100 DEP, and I started from 10. So this is approximately 7 gigahertz of energy that this discipline is covering. And so there are a lot of instruments that are doing the work of observing. The gamma rays cannot penetrate our atmosphere, so our atmospheres have to detect gamma rays in a different way. So in the ground test we have imaging Cherenkov detectors, such called there are several like the case magic or CGA. And in the space we can just detect gamma ray directly using electron positron pair compression. And that is the principle for like the Fermi telescope or the Agile telescope. So these are actually observing gamma rays. The gamma rays are looking for such of new sources and things. So what actually they have accomplished? So I want to talk a little about that. So first we know that gamma rays are produced in interaction between accelerated charged particles and interstellar target material or magnetic fields or radiation. So these target materials can be just gas, interstellar gas or ISM, from which there can be either drenched gamma ray can be produced or sort of pi decay, pi 0 or pi plus minus decay. Actually pi 0 decay. In magnetic field there can be synchrotron emission, and in radiation field or photon field there can be inverse compound emission, and all of this we can infer by multi-level studies. And the determination, the observation of all this actually tells us about the spatial and energy distribution of high energy charged particles in the universe. So, but this is a preliminary, but there are also new opportunities. For example, the gamma ray tells us about the physics of relativistic outputs. For example, if you consider AGN jets, then we can get very much information about the using gamma ray observations. And there can be probes of extragalactic radiation or magnetic fields using, for example, synchrotron or inverse compound signals. And cosmic gamma rays are also recently have been proposed that they are also indirect So, this is basically I want to touch briefly what actually the gamma ray spectrum is. So, this is what the usual Maxwell spectrum as I just said. So, the gamma spectrum actually is a sort of double amplified distribution like this. It is actually power law. It starts as a power law, as I said, but then there are several loss mechanisms which actually change the slope of the power law, and these are called turnover and the slope changes. And this happens for the synchrotron emission at higher energies. This can also happen for the inverse Doppler emission. So this can actually we can calculate basic things analytically, but before that we can and the analytical distribution is also available. So this is for electronic emission, but one can also derive these things for electronic emission. So this is basically the telescope that I mentioned. So what is the reliability and how much they expect to perform and all that. You can see that the RF fan is actually in the lower energy range sort of. But if you go to the even higher energy range case, and recently the upcoming Telecom telescope, they will probe our wide high energy range, and with that we can probe what happens in the high energy region. So what have been the main science results so far? So which have been, as I mentioned in the very first slide, very second slide, that there are three main components are discovered. One is the galactic diffusion. It is basically charged particles. They are interacting with the cosmic rays. They are actually interacting with interstellar gas and radiation fields, and they are doing brainstorming and all that, and they are emitting gamma rays. There are individual sources like pulsars or coherence or like that. They can emit copious amounts of gamma rays. And there is also a trend of isotropic diffuse emission all over the sky, which they look very low compared to the Earth. We can recently there has been some work about the origin of cosmic gamma rays, and for galactic gamma rays, the very best way to generate them is supernova reactions, because there are the presence of large shocks and diffusing shock acceleration. So if ultra-relativistic electrons or magnetic fields are present, actually they are constant by research, then they can produce such kind of cosmic rays. The Leo supernova rays are particularly suitable for accelerating cosmic rays to very high temperatures. Also, these gamma rays are also used in search for dark matter particles, because gamma rays are expected to be produced in dark matter annihilation and background signatures. So in dwarf stellar galaxies or galaxy clusters, people want the gamma telescopes at them to see the radial signatures of dark matter. And this is actually just a very big listing of what kind of sources have been discovered by the several telescopes. So you can see the active galactic nucleus here at the top, and among them the particular subclass called layers. I will talk about them in the second part of the talk. So the layers are particularly power efficient in emitting gamma rays, and there are also non-layer types. And we also get some from supernova remnants and X-ray binaries, and even like normal galaxies have power detections. However, we must note that most detections are unidentified, and there is ongoing research to see what kind of sources they are, how they are emitting their own. It is very active. So that is the foreshort of this kind of research now. For example, the gamma detection there is from star-crossed galaxy. This actually helps to probe the intermediate range of distances gamma ray luminosities, because these star-crossed galaxies are not very far away, and they have intermediate range of luminosities. So we can probe the intermediate range of galaxy distance and luminosities with them. There have been large number of pulsars observed, and there is another application is that if you can detect the network of millisecond pulsars, then there has been a recent application that the passing of the gravitational waves can be detected through them. Because of this pulsar time scale is very precise, and even if the wave passes, it changes slightly. So if you monitor that, we can check that okay, so gravitational wave has passed through them. As we have also detected a lot of gamma we can do the test of general relativity and all that we are responsible. So these are the sort of things that the Gamma community has been doing so far and is doing. So there is also a very interesting connection between astroparticle physics, which is the probing the source of neutrino level spectrum. So the principle is very simple. So neutrinos can be only be produced via hadronic decay, like a 5% decay. However, gamma rays can only be produced. Gamma rays can produce either in pi zero decay hadronic, or they can be produced by electromagnetic process, like synchrotron infrastructure. So if we detect the gamma ray from the source, we cannot conclude sufficiently that it has to be a positive accelerator. But if you also detect neutrinos, then you can definitely conclude that. So gamma ray telescopes actually tell us that where and when to look for neutrinos. And this is another application that gamma ray surveys are being used right now. So that is also under the discoveries and stuff. So now I come to the second part of my talk, which is the gamma ray emission from lasers. So lasers are actually agents with jetted agents with jets at observable levels. Right? So they are very good gamma ray candidates, and we call them lasers. Most of them are lasers. So what physics questions are there? So there is, we do not understand first of all how the jet falls. There are various models, but none of them actually explain all the data satisfactorily. So how is the jet forming? What is the particle? Jet is a class of charged particles. So what is the particle population of the jet? What are the emission processes that go on? So to do these things, we always have two things here. One is the light stuff, and another is the spectral energy distributions, and we have to make it. For example, in the previous the picture that I showed in the very beginning, there is so many sources of lasers. They are all sparkling. So lasers are actually very good gamma ray candidates, and we ongoing gamma ray observations, we can get a lot of data about them to constrain the physics. So light curves, so they are basically just we look at the variation of the flux emitted from them as a function of time. So from light curves, you can get a very useful quantity, which is a correlation among different bands. So what is that? Now suppose you look at the flux in gamma rays. So say in the month of October, the gamma ray emission is decreasing, while in November the gamma ray emission increases. Now we also need to see whether say look at another band, say X-ray or optical, whether the gamma ray emission there also decreases in October and also increases in November, or is there some lag between the rise and the fall? And actually some interesting things can be concluded from this. For example, if there is no lag between the two bands, then one can say that okay, then the two emissions are being produced in the same region, and if there is a lag, then they are being produced in the different regions, and due to light travel time lags, there is a certain lag. So we can prove the correlation here, and a very good way to prove the correlation is a thing called the discrete correlation. So it is designed for analyzing unevenly sampled data, which is doing very because say you observe a gamma ray source over say the entire week, then you just take a break over the weekend and then to observe it over again over the entire week. So there are gaps in the data, and usual correlation functions, for example Pearson or other the unmean correlation functions, they cannot do this kind of analysis. So that's what the discrete correlation function comes into play. So it was first introduced by Maitreya and colleague back in 1988, and it is actually derived from the unmean correlation function, which is defined like that. So it is derived like the UDCN, and you can see for the AI and DJ are the data points of say two bands, and then from that by doing a time meaning on that, the discrete correlation function can be obtained. And it is a very useful tool in concluding physical results about the source. So for example, there are some example correlations. These are very high energy like the EVs order gamma rays with hard X-rays. And you can see that there is a significant peak of the correlation coefficient at 0 level, which means that very high there we can conclude something that they are actually produced in the same region or not. And actually one analysis is related to conclusively assert this, but this can be this can be started as a preliminary starting point. So that's the importance of the correlation function that is here. And another very important thing is the power spectral density. So what is that? It is basically the Fourier transform of light curves. So transfer the Fourier in the light curve, the x-axis time. So here the x-axis has to be frequency. So basically it tells us what is the distribution of power emitted at different frequencies in the variability. So usually it is observed for the power source flow, and multi-level studies of power spectral densities can provide important information about, as I said, the different emission regions and mechanisms in layers. So now I will go to our original work that I have been doing, because now I have covered our tools and the things. So that is the laser called BLR. So it is an IBL plus laser at a rate. It is pretty close at a redshift of 0.7. And as our laser shows very high amplitude and rapid variability. However, what's interesting is that very recently, in 2020 to 2021, it underwent an extreme flaring, which means that the flux suddenly it was low and then it suddenly increased a lot. So what caused that? What causes a sudden increase in flux over after a long time when there is low flux? There can be changes in magnetic field. There can be changes in the particle population of the change. There can be also some part of shock propagation and things like that. So we need to prove that. So there has been one study on the flaring episode which has been on motivation so far. So they actually started to explain this thing from the context of magnetic reconnection, and they have sort of succeeded so far in explaining some observation but not all. That's why we are looking at it. So for example, you can see this is the light. As you can see here in the end, there is a very much increase in flux. Say about 59,000 LTD, there is a very much increase in flux, and before that everything is quiet. So why is that? What causes such a sudden increase in flux over such long days of quiet? So basically we are interested in this state. As you can see, it is a marking path of the S, which is what the cable community called the flaring state. And actually what causes that? So a good way to always go for some multi-level data. So you also look at X-ray data. So for that flaring state time, if you also observe in X-ray, you can see this kind of. And as well as we need to look at the correlation to see actually what is the correlation between gamma rays and say X-rays. You can also look at other events, for example. But for this kind of lasers, gamma rays and X-rays are the same. So if we do that, we find a very interesting thing. You can see there is a very prominent DCF peak at 0 days. So that is what we are seeing from result, because suggests that the gamma ray and the X-ray originate in the same region, right? Because otherwise there will be a lag due to the Webber travel time. If they are originating at different regions, then after one comes, the other one will come at a slight later time, and there will be a lag. But there is no lag here. The lag is at 0 days. So that's why the gamma ray and X-ray originating at the same region, and that actually provides a good constant in fitting the spectral energy distribution of this kind of this layer. And that is so the spectral energy distribution, I just want to touch that it should be like this double hump that I just mentioned. The first hump is for synchrotron and the second hump is for inverse compound. And it shows that the second peak should be possible to model using only synchrotron cell compound. Synchrotron cell compound means that the synchrotron photon is emitted and then it interacts with the electron to cause the inverse compound emission. That is synchrotron cell compound. But why are we considering that? We need to look at the physics. So the physics is that suppose relativistic electrons are emitting data with the top first using synchrotron and second using synchrotron self compound that will tell us about the optimal field parameters among the magnetic field, the particle proportion, etc. Which is the things that we started out to know that what is exactly causing this flaring. So that is our plan. So that's all I have to say pretty much. I would just end with the fact that the gamma is actually offers several frontiers of physics. And for example, I just mentioned one of them, which is the physics of Galileans. So that is we need to keep an eye on that because several discoveries are being made. And let's see what we can do. That's all.
So any kind of random data, calculate the correlation, we will definitely get peaks.
Yes, but these are not some kind of random. These are
No, but that is a general scenario for random. The correlation will be maximum at zero, and then it will be.
yes.
So what is the significance of, what is the specialty of this?
Yeah, because I think because in this kind in this kind of randomness is much reduced. So here we can say that since the black and two wavelengths is zero, we can say that they are being produced in the same emission. That is our conclusion.
You just in your computer you just generate say 1000 random numbers.
Yes.
And calculate the correlation. So you will definitely get the peak at
Yes, but that is if we have random numbers. But here we are not using, but we are using the observed data, right? These are not some string of random numbers.
that I know. But what is the significance of this zero peak position?
Yes, so that is the thing. The peak position is zero. See, actually, I'm not exactly sure about the aspect of randomness that you mentioned, but this much I know that this BCF thing it actually does something to reduce this sort of peak at zero plainly due to randomness of the data. So here we can conclude that, as I said, that this is not entirely due to randomness and that the emission is being generated. I don't think this is entirely due to random because we studied a lot of other as I said, other wavelengths and there we did not get such a correlation. But as I said, if there was related to a randomness effect, then we will get a zero peak in all such cases. But we did not get such peak in all cases, but only in this case.
Even in special correlation, you will find that zero will be peak at zero and then it will not only in special
Yes.
anywhere in the
Yes.
will be peak at
Yes.
So one quick question, you have mentioned the discovery, like that part is peaked by aging. Any such particular reason for that?
Yes, that is because they are first of all they are as I said, they are people layers. So that is because they have the jets pointed at us. So you know about electricity that the radiation gets much magnified because it is coming directly at us. So that's why we can detect so much of them because we are actually observing such kind of sources that are magnified scale. But say we say normal galaxy or things like that, they are not always being at us, right? So we are observing them at the regular luminosity. But for AGMs, we are observing them at an increased luminosity, magnified luminosity. And that's why we can detect them so easily.
this BCF is basically the Pearson correlation.
Yes. 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 Often we actually compare the DCF results with the Pearson.
It can be shown analytically.